about 12:30, so we're probably going to get started. Just so everybody's aware, this is for Statistical Methods I, so if anybody's in the wrong place, you know. All right, so first off, chapters 1 and 2, it was mostly just vocabulary. I think the biggest part was when we're looking at the distributions, right? We wanted to figure out the relationship between the mean and the median, depending on what the shape of the distribution was. So if we go ahead and draw a right skewed distribution, right? Looks kind of like that. So how should we compare the mean and the median here? The mean is greater than the median? Yes. Did I get that? And then left skewed is just the opposite, right? And then when we're looking at symmetric, we have this, right? It's like mound shape, bell curve, whatever you'd like to call it. And then we could also have more like a uniform distribution, right? And here, how were the mean and the median related? Equal, exactly. Okay. So then, getting into an actual question, if you look up here, the GRE scores of UCF's graduating class have a symmetric distribution, so we know it's going to be either of these two, right? The average score is 290 and the standard deviation is 8. If a graduate school wants to admit students with scores in the top 16, what should be used as the cutoff score? So what does this sound like? What kind of problem? We're back to chapter 2. We had empirical rule and Chev's rule. Which one does this sound like? It's empirical rule. Right? What do we have here? 290 would be in the center, right? Because we know the mean and the median are equal. So it's right in that middle. And this would be one standard deviation away. This would be one standard deviation away. Okay. So what percentage would be within this one standard deviation based on empirical rule? 68%? 68%? Exactly. And that would mean that 16 would be on this side, 16 would be on this side. So if a graduate school wants to admit students with scores in the top 16%, which score should be used? 298, exactly. Okay. That one. Now, if the distribution of the scores was unknown, what proportion of scores would be at least 306? And we're assuming that the mean score and the standard deviation remain the same. So our mean score before was 290, right? and the standard deviation was 8. Now the distribution is unknown, so what shape is we're going to be using? Empirical rule, Chevy, Chev. Which one? Chevy, Chev, exactly. So just something like this. Now we're looking at 306, right? You see that? Sorry. So this is our mean. And we said in the last part of the problem, this was 1 standard deviation away. If we did 2 standard deviations away, we have 306 right here. Right, so this is what we want. So when we're looking at Chevy Chevs, we have to consider what K is, right? So what would K be in our case? Let's look at right here. Yep. So again, we'll just put these on the remember, K represents the number of standard deviations, right? So does anybody remember the rule? To which way? The other way? Okay. So when it comes to Chevy Chev's rule, does everybody remember that at least 3/4 of the distribution is within 2 standard deviations from the mean? So if we have at least 3/4 of the distribution within 2 standard deviations, right? This would be at least, right? 75% is just 3/4. And we want to look at everything here, right? If we want at least 306, we want everything that's greater than 306 or 306. So to be no more than 25%. So in a group of students, 56 of them have poor vision and use glasses. 33 of the students also have contacts as a backup. Given that a student uses glasses, what is the probability that they also have contacts? So just this given that right away, we know that it's going to be conditional probability problem, right? So if we go to here, can everybody see this? So the probability of A given B. So this line right here, that's our condition. So let's write that up here. Okay. So what is event A? What do you guys want to call that? The glasses? Okay. What would be B? Would it be both? Why don't we draw a Venn diagram? So we said event A is that they wear glasses. What if we said event B was that they wear contacts? So what would be the intersect then? They wear both. So it tells us that, right, 33% of the students also have contacts. So they have glasses and contacts. So we know that this intersect right here is 0.33. Now the entire circle has to add up to 56, right? When it comes to these Venn diagrams. So this right here would then be 23, just glasses. Okay. So they didn't tell us the percentage of students that just wear contacts, so we don't know that. And we don't know the percentage of students who don't wear either. So we actually should change this and we know that, again, the 56% wear glasses, says it in the problem. 33% wear both. Okay. Did everybody get the answer? It's 59%. Okay. Okay. So this is another probability question. A certain moviegoer will only leave a movie a maximum of 2 times and will only leave to use the restroom. The moviegoer will go to the bathroom during the trailers 80% of the time. If he forgets to go during trailers, he will go during an emotional scene 60% of the time. If he does go during trailers, he will also leave to go during an emotional scene 30% of the time. So what is the probability that he goes both during trailers and during an emotional scene? So are these events independent or dependent? Independent? It actually would be dependent, because if he forgets to go during trailers, he's going during an emotional scene. If he does go, I mean, he will go during an emotional scene, but for a less % of the time. So whether or not he goes during an emotional scene depends on if he goes during trailers. Does that make sense? So let's call event A that he goes during trailers, event B that he goes during an emotional scene. So what is the probability that he goes during trailers? It says it in the problem. Exactly, 80%, so 0.8. Now, how could we write that 60% of the time, if he forgets to go during trailers, he will go during an emotional scene? All right, let's think about with the conditional probability, right? We have that line, it represents the condition. So given that he forgets to go during trailers, he goes during an emotional scene. So we have emotional scene as B. This is our condition. He forgets to go during trailers. He's not going. So this would be a complement. Does that kind of make sense? And that would be our 60%. Okay. And then if he does go during trailers, he will also leave during the emotional scene 30% of the time. So given that he goes during trailer, he goes during an emotional scene 30% of the time. So if we go back to the Venn diagram thing, the question wants us to find both during trailers and during the emotional scene, so we want to find the intersect. And then if we go back here, the formula that you have for that it's a good formula to keep in mind. I would definitely write it on your formula sheet if you haven't. It's when you have dependent events like this, the probability that they intersect, that both event A and event B occur, this is just the formula for it. Right, so we have all these values here. Just plug them in. Everybody get the answer? .24, exactly. Right, 24%. Okay. All right, I'll leave that up a little bit. We can see the next one. Okay, so the next couple are kind of like the counting rules, just in case if you guys need them. So we have 9 blocks. They are numbered 1 to 9. If you are selecting 2 blocks, how many different 2-digit numbers can you create? So what type of problem actually would this be as far as a counting rule? Would it be combination, permutation, or multiplicative rule? Okay, so with combination, the order doesn't matter. With permutation, the order does matter. So in our case, if we're making a 2-digit number, does order matter? Okay, so order would be like, right, 1 and 2. Would this make a difference in the number? Yes. So order does actually matter in this case. So this would be a permutation. Okay. All right, so I'll write that. So order determines the number. So if we're doing a permutation, some calculators you just have to do the setting, 9, choose 2. What did everybody find? 72. Yeah. Okay. There is a formula for it. Unfortunately, if we have time at the end, I'll get back to that. So you are creating collages using 53 distinct pictures. If you want each collage to contain 6 different pictures, how many collages can be made? So if we want 6 different pictures for each collage, would we have replacement or would we not have replacement? No replacement, right? So without replacement. So we know it's not going to be multiplicative rule. So it either has to be combination or permutation. Okay, so in this case, does order matter? No. Just say no order. Like, it's not important. So in this case, we know that it's going to be combination. And for anybody who does, who's not sure how to do the setting on the calculator, the formula for combination, 53 factorial, 6 factorial, everything in there factorial. What did everybody find? Yeah, it's a large number. Good with that one? All right, so next one, a baseball coach is selecting 9 players out of the 40 that are on the team to put out on the field. How many different selections are possible? So out of all the counting rules, which one would this be? I heard someone say it's combination. right? Because changing the order of the players, it wouldn't make a difference. So order is not important in this case. So we have 40 because there's 40 players, and he's choosing 9. So again, it's a large number. So I guess the biggest thing with that is just identifying what type of counting rule it actually is. So the next one goes back to the discrete random variables, right? We have 70% of the people in the United States, they have diabetes. If a researcher takes a sample of 3 people, what is the probability that exactly one of the 3 who are sampled does not have diabetes? Right, so we have a sample size of 3. And for this case, are we looking at a binomial X random or a Poisson? Okay, so binomial X, we have a success and a fail. When we have Poisson, we have an average. Do you see average in the question at all? No. So it actually is a binomial, and we could consider our 70% as our success, right? So our variable in this case would be the number of people with diabetes. Okay. So let's call our success, again, the number of people with diabetes. So that would be our 70%. That would make our fail 30%. Now it wants us to find the probability that exactly one of the 3 does not have diabetes then. So we have a sample size of 3. Subtract the one without diabetes, and that would make our X 2. All right, so probability that X equals 2. Now you do have your tables for the binomial X, however, because our sample size is so small, we actually can't use those. So we do have to use the long formula. Right? And that is, okay, I didn't put it up here. Can everybody see that? Okay. So and then you just plug in the values. There, we'll see. And then this would just be 1, right? So combination 3, choose 2. We know that that's just going to be 3, right? And then this would just be 0.49. Anything raised to the 1 power is just 0.3, whatever the number was before. So you should find that the answer is, so basically 44%. All right, so within a particular small town, an average of 13 911 calls are made per day. What is the probability that at least 7 calls are made on a given day? So again, if we're looking at either Poisson or Binomial, what should we know based on what's given in the problem? Yeah, it's Poisson, average. Right? So something with Poisson, right, we saw this symbol lambda. That's basically our mean, average, so that would be 13. We'll call our variable x the number of calls. So we want to find the probability that at least 7 calls are made on a given day. So, right, greater than or equal to? Has to be 7 or more. So this one, we could use our tables, right? So if we go there, the only thing is, what do the tables, what values do they give you? Yes, I heard someone say it, less than or equal to. So how could we manipulate this so that we could actually read off of the table? Yes. Exactly. Okay? Because we want all of the values that are greater than 7, so we're just going to cancel out everything that's less than or equal to 6. So what did everybody find? Everybody find that? Okay, so if we go to our tables, we see 13 right here, right? This is our lambda. This was our average. And if we're going over to 6, that's our k, right? Yeah. We're looking at Poisson. Are you looking at where it has n equals at the top? Yeah. So if we look, I hope you guys can see this. Okay. So we have our lambda. That's just basically what our average is, right? We said that it's 13, so we go down here. 13 is right here. And then our k, we're looking at what's the probability that at least 7 calls are made. And we said before, when we're looking at the tables, we have to use less than or equal to 6 in this case. So we go over to 6 right here. Okay. Everybody good with that? Okay. So next chapter dealt with standard normal variables, and we are finding z-scores a lot. This becomes really important in the later chapters, so it's good to get this down. Right, so we know when it comes to these, we're always going to have a bell curve. And again, we went over this before. The median, the mean, it's right in the middle. And the z-score of the mean is always 0 because the z-score represents the number of standard deviations away from the mean. If we're at the mean, nothing is going to be deviating. So what's the probability that the z-score is greater than 107? So let's see, if ours, let's put 107 right here, right? We want to find the probability of over here, everything that's greater than that. Okay? So depending on what professor you have, you could either have the negative and positive z-score values, or you might have these, where you're going from this 0 to whatever z-score that you have. It gives you this area right here. So if you do have this type of z-table, you should find we had our z-score of 107. Yeah, 3577. So that would go right here. And something that I didn't mention, if this entire thing represents 100%, this would be 50 on each side, right? 50 and 50. So you just subtract 0.5 minus, and that would get you that shaded area that you actually want. So you should find, now if you have the positive, negative z-tables, I would just look up negative 107, and then that would just get you, because again, they just reflect. This is a symmetric distribution. All right, and then if we wanted to find the probability that z is greater than z naught, if that actually equals 0.51. So we actually want to solve for this z naught. In this case, it already gives us the probability. So let's draw another distribution. We have our z right here. So like I said before, if right here, this splits it half and half, and our probability is 0.51, we know that our z naught is going to be negative. Does that make sense? Because everything greater than this, we're looking at all of this area right here. So what should we look up on the tables? If we go back here. Again, we're going from that 0 to whatever area that's shaded. So we'd actually be looking inside right here, finding that 0.1. Right? It's pretty close. So if you just average 0.25, 0.26, you should find yes, you're right. Okay, so next one, let x be a normally distributed variable with a mean of 400 and a standard deviation of 35. What value of x is in the 75th percentile? So we're drawing the distribution. We have 400 as our mean. Again, this would be 50%. So then if we wanted to find the 75th percentile, we're just adding an additional 25% onto that. And this is what we're solving for. So what z-score would correspond to this 75%? Again, if we have these, we would just be looking for that 25 right here, okay? So you'd be looking inside, and then we'd go up the columns and the rows to find the z-score. So should be 0.675. And then to go from the z-score to find the actual variable, right, we have this formula. And then we just plug in the values. And again, that makes sense because if this were 1, then this value should have been 435, because it would be 1 standard deviation away. But it's not quite 1 yet. Yes, I'm sorry. This one?
Yeah, how come it's not 0.01?
For the z-score? Oh, I see what you mean, because this would make this 60%, or right? Like if this were, then that would be the correct answer. We change that to the probability that z is greater than z naught equals 60%. Cool. Sorry. Okay. Okay. So the mean number of times a family goes out to eat per month is 12, with a standard deviation of 3. A sample of 45 families took a survey, and the average number of times they went out to eat was 9. Are you surprised? So this is when we actually have to start getting a little bit more logical. All right, so this is kind of like chapter 6 stuff, where we have what's given with a population, and we're kind of going to test that. So our population mean would be 12 then, right? And then what would be our mean for the sampling distribution? I'm sorry? It is 12. Right, so these are always equal. When you said 9, that's just the sampling mean, x bar. That's what we're going to use to test if whether or not we're surprised. Okay. We have our standard deviation. Population standard deviation is 3. So if we wanted to do the sampling distribution standard deviation, how should we find that? Yes, exactly. Okay. And that would just be 3 over the square root of 45. Okay. So if we were to draw it, okay, just remember that that's 0.447. Then draw it over here. So we have our x bar. Okay. So when it comes to the standard normal z-score, or this distribution, usually we don't like to exceed 3 standard deviations. So if we had our z-scores, right, we don't want to exceed 3 on this side, we don't want to exceed 3 on this side. So the actual variable that corresponds with the z-score should be 10.66. Okay. Now, if we want to figure out whether or not we're surprised, we should find the z-score that corresponds with this mean. Okay. All right, and then that formula, again, it's just what you guys have been doing. I mean, that's something that we learned like chapter 1 and chapter 2. The only difference being this is our standard deviation now. So what did we find as our z-score? Negative 6.7? All right. So should we be surprised? Do we think that this is likely to occur? No, right? And then, I mean, just going back to this distribution, 9 would be all the way over here, right? So it's way out there. And again, we don't want this z-score to exceed negative 3. But it's negative 6.7, so. Okay. All right, so if only one family is randomly sampled, what is the probability that the number of times they go out to eat, it should be less than 4?
For the last one, so are you surprised or are you not surprised?
Yes, you're surprised, because that's not likely to happen if it's way outside of that distribution. The negative 6.7, that would correspond to this 9, that mean, that sampling mean.
Based on that, what is the information based on z-score relating to sample?
3 deviations away from the 12 is the negative 10. That's what I'm getting from this. On your, yeah. On
So if we have a z-score of negative 3, that would be like that, like minimum of this distribution. We'd have, I guess the number of times that they go out to eat per month would be 10, like a little over 10 and a half times, right? But this sample that they took, they only found that the number of times that they went out to eat was 9. So it's not going with whatever information that they're getting up here. The mean number of times they go out to eat is 12. Yeah. So this would just basically be, I'll write it up here. This 10.66, it's the mean that we have right here, that 12, and then 3 times the standard deviation that we have, right? And then same on the other side, we're just adding. Okay, so if only one family is sampled, what should the probability that the number of times they go out to eat is 4, or less than 4? Right, so let's draw the distribution again. All right, we have 12 in the middle. And if we're only sampling one family, our sample size is just 1. So basically our standard deviation would just be 3. And we're just finding the z-score. So this would be our x bar. So we found our z. It's going to be over on this side, negative 2.7. So we want to find the x that corresponds with that z-score. So again, we have to go to the tables. Wait, what did you find for the z-score? .496. So for this area right here, you got 49. Right, and we want to see number of times that they go out to eat is less than 4. So we want to find everything that's in here. So again, everybody good with that one? Just subtract the 0.5 from the 0.4965 that we got. Yeah. Because if we're looking at 4 right here, we know that this is going to be less than the mean. It's just more position stuff. It doesn't really matter when you're looking at the z on the z table. Okay. So a restaurant owner is estimating the mean amount of time it takes for a customer to receive their meal after ordering. Assume the standard deviation is 4.6 minutes. Okay. After observing 90 customers, the average waiting time is found to be 23.2 minutes. Construct a 92% confidence interval for the true percentage of the mean waiting time. So I believe your professors have given you like the z-score that corresponds with like a 95% confidence interval, 99% confidence interval. However, I don't believe 92 is one of them that's given. So just so that you remember how you can actually find that. Right, so if we split 92 in half, be just 46 on each side. And then you just go to the z-tables and you find the z-score that corresponds with the probability of 46%. Yeah. All right, so this problem's kind of wordy, so I'm just going to, these are the variables that we need in order to figure out the confidence or the interval estimate, right? And the standard deviation. We already know what our z-score is. We know that this is 90 based on the problem. So, just a reminder, this is the formula that we need. Okay. And then we're just plugging everything in. So if we're just calculating the sampling error, right? This is everything that encompasses what the sampling error is. What did we find?
485.
Yeah. And then if we want to find the interval estimate, we would have a minimum right here and then the maximum right here that's within that interval. So we're just adding the 0.85 to our mean and then subtracting the 0.85 to our mean. Everybody good with that? All right. So using the information from part A, what would be the interval estimate for the waiting time if only 18 customers were sampled? Instead, this time though, we're going to be using a 90% confidence interval. So only 18 customers are observed. So what's going to be different about this problem versus the last? Yes, the n, right? Does that mean that our calculations are going to be different as well? Yes. Right, because for the last one, we had our sampling size greater than or equal to 30. When our sampling size is less than 30, we're going to be using the the t tables. T. Okay. So with the t tables, you have to find our degrees of freedom, right? Yeah, 17. Okay. And then if we wanted to right, if we have 90, Right, because when we're looking at the t-tables, we only really have to keep in consideration the tails. So just going back to this, just a quick refresher. We said our degrees of freedom were 17, so we're looking right over here. And if our tail, if we have a 90% confidence interval, each tail is going to have 0.05. Right? So it should be 1.74. And the formula to find the interval estimate, it's just the same as the last problem. We're just substituting the z for the t this time. And, well, the standard deviation is going to be different in the n, but we're still using the same variables. What did everybody get? 8.86? Plus or minus? That. There we go. Okay. And then again, just like the last one, to find the minimum, subtract 1.886 from this 23.2, and then add in order to find the maximum. So the decimal should be here. Yeah. We were right the first time. Okay. All right. And then again, this is just another part to this problem. So how many customers should be sampled in order to have the mean waiting time estimated up to 15 seconds with a 92% confidence? Okay. So what is this up to plus or minus 15 seconds? All right. I didn't hear a definite answer. I wasn't really sure. Sampling error? Yeah. So this is our okay. So in order to solve for n, and this is posted on the Study Union website if you want. So we're basically, I just did like a kind of like a flow chart type thing when we want to solve for the confidence interval when we have a large sampling size. We're using this, and that's what we just did in the other problem. And then these are just the formulas that we're using. So if we want to solve for n, we're going to be using this right here. Okay? So we have and we know the z that corresponds with the 92% confidence, right? We already found that in part A. Yeah. And the standard deviation was given. And we said before, our sampling error is 15 seconds, but was our mean in seconds or was it in minutes? It was in minutes. So we have to convert those seconds into minutes. So 15 seconds is what fraction of a minute? Yeah, 1/4. Okay. So what did we find? Yeah, and just know for these, I mean, I'm sure all of your exams are going to be multiple choice. Always round up though, because the answer is actually like 1,036, yeah, 0.84, so round it up. Okay. Next one. Okay. In a sample of 345 driver's ed students, 262 of the students passed their final driving test. So we have to construct a 90% confidence interval for the true percentage of students who passed. Okay. So right away we know it's going to be a proportion. It already tells us that. We know n is the sampling size. What is our x? Yeah. Okay. Yep. 76%. So that's the percentage of students who actually pass, which would make the fail, right, 24. It all adds up to 100%. Okay, and then just going back to here, right, we know our n is greater than 30, so we know we're going to be using the z-tables. Okay, so this is our formula. Okay. So we'll just plug everything in. And what's the z-score for a 90% confidence interval? I think this is one that your professors gave you. So the sampling error should be, did everybody get that? 0.0378? Okay. So that would mean that we are 90% confident that, right, the true percentage of students who passed are within, what, 72% and like around 80%. If you wanted to say it in words. All right, and then the second part, how many students need to be sampled in order to create an interval estimating the proportion of those who passed to have a width of 0.09 with 99% confidence. So that one's kind of wordy, so let's look at it in parts, right? We definitely, this is really important, and this is important. And we know we want to find how many students, so we know that we're going to be looking for the sample size. So our formula then should be right here. N equals z squared times p times q over the sampling error squared. Okay, so does it tell us what our success and fail is in this part of the problem? No. So if it doesn't tell us what P is, what can we assume? Yes, exactly 0.5. And then that would make, if there's a 50% success rate, then we know that there's a 50% fail, right? 50-50 chance. And then the 99% confidence, that's one of the z-scores that's given, right? Yes. Right, and then 5 times 5 is just, or 0.5 times 0.5 is 0.25. Now, what is our sampling error? I'm sorry? 0.09? Okay. So this one's a little tricky. It tells you that the width is 0.09. So yes, 0.045. So if, just to explain that really quickly, the entire interval width is 0.09. And we know that when we're doing the interval estimate, it's plus or minus the sampling error. So we're subtracting on this side. We're adding on this side. Oh, I don't know why I did that. Right? So this entire thing is 0.09. It's kind of like if we drew on a number line, we have our mean here. We'll just say that this is our mean. Let's see. Right, so this entire thing would be 8. If you want to think about the width thing. Okay? So back to this though. Solving for n. Just plug this all into the calculator. I'm sorry? Yeah. So it's 818, and then I actually found that it's 0.6. So again, like how I said earlier, you always round up. Because we can't have a fraction of a student. Okay? Next one. It is said that on average it takes 40 minutes to get ready before leaving for school or work. A sample of 70 individuals took a survey, and the researcher found the mean amount of time it took to get ready was 54 minutes with a standard deviation of 6 minutes. is this evidence to show that the claim is too low? So this is definitely a chapter 8 problem. Right, we're testing the hypothesis. And whenever we had these, we had a null hypothesis and an alternative hypothesis. Okay? So it's saying on average. So, yeah, exactly, mean. So with these, we're looking at a population mean when we're looking at the hypotheses. And I always like to think the null is something that's set in stone. So it's always going to be equal to. Period, no question about it. But the alternative is trying to say, no, that's not correct. It's different than that. So what is our population mean equal to? 40. Exactly. Right? It says at the first statement, or the first sentence, it has said that on average it takes 40 minutes to get ready. Okay? So what would be the alternative then? So it's asking, is there evidence to show that the claim is too low? So they're thinking that the claim is too low. Exactly. It's greater than 40. Okay. All right, and then again, we'll write out all our variables that we know that are given. We have 70 as our sampling size. So let's find our z-score, the z-score that corresponds with this sampling mean, right? And that's the 54. Okay? What? Yeah. Did everybody get 19.5? Okay. So if we are to draw the distribution, it says that our alpha is 0.01. Now, this is which type of test are we doing? Upper tail? Yep. So it's going to be on the right. We're going to place our alpha on this right side. And what z-score corresponds with that alpha? Yes, 2.33. Okay. And the z-score that we calculated, it's way over here. So what should we conclude? Yes, we are rejecting HO. Okay, and again, we can see that it's inside the rejection region, right? This entire thing is the rejection region, the alpha space. And then another way that we could find that also, if this part from this 19.5 over, if that represents P, right, that probability that we actually do find a z-score that's 19.5, it's much smaller than this alpha. Because if you tried to look this up on the z-tables, you wouldn't be able to find it. It's so small. Okay. So that's another way that we just show it rejecting HO. Okay. Okay, next one. In a study, people with severe skin damage were advised to use sunscreen prior to going outside. A year after this first consultation, 42 of the people still neglected to put on sunscreen, and 49 actually did start using sunscreen. Using a 0.1 significance level, can you conclude that the majority of people with skin damage are applying sunscreen after being told to do so? So again, we're going to be doing a test of hypothesis, but this time we're not looking at an average, right? So what are we actually looking at? Proportion, right? So let's just write right away. We know our sample size is 91. Let's do that. And then let's see what our p hat is. Right, p hat is the success rate of the sampling, the sample. So in this case, what would our success be? Would it be the number of people who actually do put on the sunscreen or who do not? Who do. Right, because the question, can you conclude that the majority of the people are actually applying it? Right, so this should be 54. What would be the success rate of the population? Just normal P. Does it tell us what that is? If we look in the problem? Huh? Yeah, so does it actually tell? I'm sorry. The 42? So those are the people that are within the sample that don't actually apply it. We want to find the success rate of the population. So that should be given. Does anybody see it? Yeah. I mean, if no one sees it, then what can we assume? It's not given, it's unknown. And then what did we say based on the other problems before? Yeah, exactly. So the success rate is just 50%. Okay. All right, and then when we're looking at our null hypothesis and the alternative, right, what I said before, the null is always going to be equal to, and we basically just said that already, it's going to be 0.5. Now, what would be the alternative, though? If the question is asking, can you conclude that the majority of the people are applying the sunscreen? You think it's less? Greater. Again, because we're looking at the majority, so it would have to be more than 50%. So just like with the last one, right, we're going to be calculating the z-score. And we're just going to be using this formula that's up here. The only difference being this time, though, we're looking at a population proportion, not a average. So actually, let me get this up. It would be down here. That's the formula. Yeah. Number 15. Right here. So we're looking at, is there evidence to show that the claim is too low? We want to prove that the claim is too low. That's why when we're testing, we want to see if the mean is greater, if that kind of makes sense. Because if this alternative was correct, that the mean was greater than 40, then that would be evidence to show that it's too low. Does that kind of make sense? Okay. Okay. 0.76? Yeah. Okay. And then we go to draw the distribution. And then how should we put we said that our significance level is 0.1. What is that an indicator of? Yes, that's alpha. And then you said it's upper tail, because it's greater than. Did someone say 1.28? Yeah. Okay. Yeah, that's the z-score that corresponds with that alpha. Good job. Okay. And then we found that our z-score is 0.76, so it would be somewhere over here, right? Fail to reject. Right? It's outside of the rejection region. This is our rejection region. And then we can see, just based on the fact that because it's before this alpha, we know that the p, the probability, it's going to be the shaded area plus the alpha. So we know already that p is going to be greater than alpha. Okay? Cool? Yeah. That was the z-score that corresponded with this alpha. Yeah, so if you go to the z-tables, if you have the z-table that looks like this, right? If the 0.1 is right here, we're going to be looking at this shaded area as 0.4. So you find 0.4 inside here, and then solve for that z-score. No problem. Okay. Next one. A company claims its low-sodium crackers contain at most 35 milligrams of sodium per serving. A random sample of 15 of these crackers has a mean of 37.5 milligrams and a standard deviation of 2.7 milligrams. Is there evidence to support the claim? Okay, so first thing, let's set up the null and alternative hypotheses. Are we looking at an average or a proportion? Average. And we know that this is going to be equal to, right? Equal to what? 35. And this is going to be 35, but are we doing that it's greater than, not equal to, or less than? It's just, I would just say less than. You don't really use the less than or equal to with these.
So is the null hypothesis always equal to?
Yes, the null is always equal to. And everybody understands, right? It's less than because is there evidence to support the claim that they're doing at most 35, no more than this. It would, but however, when we're doing these tests, we never use the equal to. It's just either greater than, less than, or not equal to.
Okay, but just for understanding, is it less than?
Yeah. When you look at most, it's,
Less than. Okay.
yeah. No problem. Any other questions that I saw a hand? Okay, so, and then again, we'll write down the variables. And these are all given. Okay? So our n is less than 30. T, exactly. Right, so we know we're going to have to find the degrees of freedom when we're looking at the t-tables. 14. Exactly. All right, so let's find the t-score. And again, it's just basically the same as the z-score, the formula. We're just taking the x bar minus the population mean over the standard deviation divided by the square root of our sample size. Yeah. You put a 6 at the end? Yeah. Okay. Okay. And then we'll go to our distribution. We know that our alternative hypothesis is less than lower tail test. It gives us that our alpha is 0.05. So what is this t-score? Okay. Now our t-score, I'll put this over. The t-score that we got was positive. So right off the bat, we could have figured if this is a positive t-score and we're doing a lower tail test, we could have determined that already it was outside of the rejection region. Exactly. Okay. Good with that? Yeah, when you're failing to reject HO, there's not enough evidence to show that the alternative is correct.
And what's the other reason that it fails to reject?
Oh, okay, so you're more supporting towards HO than HA. Okay, so failing to reject HO means rejecting HA.
Yes, here, I'm sorry, I didn't write HO. There we go. And you said with there's another way you wanted to figure that out. So if we have P is greater than alpha, we never reject HO.
Wait, isn't there one where it's like if it's equal to?
I'm sorry?
It's like something like equal to, like P is equal to alpha or something.
I wouldn't worry about that. I haven't heard. Just knowing that when P is greater than alpha, don't reject HO. If P is less than alpha, like how we had with problem 15, when P is less than alpha, we're rejecting HO. All right. And then the last one, this is the most recent chapter, chapter 9. And just to show, again on that WordPress, Study Union WordPress site, I made like a flow chart. Oh, it's kind of hard to see it. Just of the formulas to kind of keep it straight, because I know that there are a lot. Okay? Anyhow, a study was run to see if there's a difference in mean test scores between students who eat breakfast and students who skip breakfast. 17 who ate and 19 students who did not were studied. The mean grade of the breakfast eating group was 89 with a standard deviation of 6, and the mean of the breakfast skipping group was 81 with a standard deviation of 7.5. Is there enough evidence to conclude that there is a difference? Okay, so with these, I always like to write these out, definitely to keep it straight. Okay, and these are all given. Now, our alternative and our null. So the null, it's always going to say that the two groups are the same. There's no difference between them. Okay? So essentially we could write this. Because if we add the population mean of the second group to both sides, then they would just be equal. Okay? Now this question is asking, is there enough evidence to conclude that there is a difference, though? So then, if we're saying that there is a difference, they would not be equal to. Okay? So, just like with the other problems, we have to look at our sample sizes. They're both less than 30. So we know we're going to be using the t-tables. And the formula to find the actual t-score we have to find what SP squared is also. It's in one. I'll fill that in a bit. So again, that's just something that's right here, if everybody can see that. And then in order to find that SP squared, right, our sample sizes are not equal to each other, so we have to plug that in. Sorry. Did everybody get this? I know it's a long formula, so it takes a while, but okay. So going back to here, Did we all find that as a T? Okay. And then again, since we're using the t-tables, we do have to find the degrees of freedom. So I'll do it up here. So you get 34. All right, and since we're doing not equal to, the test is going to be two-tail, right? And our alpha is 0.05, so we're going to have 0.025 on each side. And then the t-score that corresponds with that? Should be, okay. And we found that our t-score from up here, right, it was 3.5. So that would be somewhere over here. So it's inside the rejection region. Yep. If you look on your t-tables, that's what corresponds with that alpha, right? We have 0.05. You have to split that onto the two tails because it's a two-tail test. And if you go on here, if our degrees of freedom are 34, we're looking at right here, and then 34. So we don't actually have a 34 on here, but if you average, right, we have 30 and 40. In between these two. Okay. All right. So it is 2:30. So I'll leave you guys with that. We also have the other sessions are streamed on YouTube. I'm sorry? That was, if you go on your t-tables, we have our degrees of freedom. If we look right here, this is the tail that we're looking at. Yeah, because we had to split the 0.05 onto the two sides. It's a two-tail test. And then if you go down, I'm sorry, right here. Because we had our degrees of freedom were 34. So if you average that 30 and 40. Oh, okay. Yeah, 34. All right, good luck, guys.